Third try is the charm. Hello, how are you? This is the participation part. Come on, you are not the first time here. Okay, my name is Dobrica Pavlinušić, and I will try to persuade you today that you can do with your Linux something which you might not have thought of by yourself, I hope. In a sense, in last year and a half, I noticed that I am using microcontrollers less and less, and that I'm using my Linux more and more for more or less the same tasks. And in that process, I actually learned something which I want to share with you today. In a sense, my idea is to tell you how to do something with your ARM single-board computer. In this lecture, we will talk mostly about all-winner boards. But if you want a hint, if you want to buy some ARM computer, please buy the board which is supported by Armbian. Armbian is the project which actually maintains the distribution for ARM boards and is currently the best distribution for ARMs aside from Raspbian for Raspberry Pi, but Raspbian supports only Raspberry Pi. But if you have any other board, please take a look if there is an Armbian port. If there isn't, try to contribute one. And if you are just deciding which board to buy, my suggestion is buy the one which is already supported. On the other hand, if you already did something similar, you might have found some references on the internet about device tree, and it looked like magic, so we'll try to dispel some of that magic today. Unfortunately, when you start playing with it, one of the first things you will want to do is recompile the kernel on your board. So be prepared to compile additional drivers if they are not already included. Armbian again here wins because it comes with a lot of drivers already included. And this year I will not say anything which requires soldering, which might be good for you if you are afraid of the heat. But it will be a little bit more than just connecting few wires, but not much more. For a start, let's start with the wording. For example, you have an small ARM board, and you want to have a real clock in it. You know, the one which keeps the time when the board is powered off, has the battery, and so on. If you buy the cheapest one from China, which is basically for Arduino, you will buy the device which is 5-volt device, which your ARM single-board computer isn't. You can modify the board, removing 2 resistors if you want to, but don't tell anyone. I2C, and we'll mostly talk about I2C sensors here, should be 5-volt tolerant. So if you by mistake just connect it and your data signals are really 5-volt, you won't burn your board, but if you are supplying your sensor with 5 volts, please double check that it's sure to connect it to your board and nothing bad will happen. This is the only warning I have for the whole lecture. In this example, I showed you a really simple way in which you can take the sensors, run I2C detect its address. In this case, it's 68. And then run load one kernel module, and all of a sudden your Raspberry Pi will have battery-backed clock just like your laptop does. But how did this journey all started for me? About 2 years ago, I was very unsatisfied with the choice of pinouts which you can download from the internet. I was thinking something along the lines, wouldn't it be nice if I could print the pinout for any board I have with perfect 255 millimeters pin spacing, which I can put beside my pins and never make a mistake of plugging the wire in the wrong pin. And we all know that plugging the wire in the wrong pin is always the first problem you have. On the other hand, you say, oh, this is the great idea. and you are looking at your pinout, which is from the top of the board, and you are plugging the wires from the bottom of the board, and all of a sudden your pinout has to be flipped. But once you write a script which actually displays the pinout, it's trivially easy to add options to flip it horizontally or vertically. And create either black and white pinout if you are printing it on laser, or color pinout if you are printing it on some kind of inkjet. So once you have that SVG which you can print and cut with the scissors and so on, it's just a script on your machine. So you could also have the command line output. And then it went all south. I started adding additional data, which you can see on this slide in square brackets, with the intention of having additional data for each pin. For example, if I started SPI, I want to see that this pin is already used, so I will not by mistake plug something into the SPI pins if I already have the SPI pin started. If I have the serial port on different boards, your serial might be UART4 on this particular CPU, but it's the only serial in your Linux system, so it will be devtty S0, for example. So I wanted to see all the data, and in the process, I actually saw a lot of things which kernel know and I didn't, so I'm today talking to you about it. Of course, in command line, because you might rotate your board while plugging the wires, you can also do all the flips and things you already saw in the graphic part. So let's start with the sensor. Okay, I said cheap sensor for eBay. We'll get to cheap sensors from eBay. But this sensor is for some old PowerPC Macintosh. It was attached to the disk drive, and the Macintosh used it to measure the temperature of the disk drive. You know, that was in the times before the Smart had the temperature. And I said, this is the old sensor. Kernel surely doesn't have support for it. But oh, look, you just grab through the kernel source, and indeed there is a driver. And this was a start. I said, driver in kernel. I don't have to use Arduino for it. So now that I know that driver is there, and I have kernel model compiled, we said that prerequisite is that we can compile the kernel. What do we actually have to program or do to make this sensor alive? Not more than this echo in the middle of the slide. You just echo the name of the module and the I2C address. The I2C address is, we saw it before, we can get it with I2C detect by just connecting the sensor. And the new device will magically appear. It will be shown in the sensors if you have LM sensors package installed. But if you don't, you can always find the same data in sys file system, which is full of wonders, and as we'll see, in a non-formatted way. So the first 2 digits, actually the last 3 digits are the decimal numbers, and all the other are the integer Celsius in this case. But you might say, oh, but I don't want to put that echo in my startup script, or I would like to have that as soon as possible. I don't want to depend on the userland to actually start my sensor. And believe it or not, because your smartphones have various sensors on them, there is a solution in Linux kernel for that, and it's called device tree. So this is probably the simplest form of the device tree, which still doesn't look scary, but it will. Stay with me. And it again defines our module, the address, which is 49 in this case, and the I2C1 interface, just like we did in that echo. But in this case, this module will be activated as soon as kernel starts up, as opposed to at the end of your boot up process. One additional thing that kernel has, and many people do not use, is ability to load those device trees dynamically. The reason why most people don't use it is because they are on 2 old kernels. I think you have to have something along the line of 4.8 or newer to actually have the ability to load the device trees live. Basically, you are you are using sys kernel config directory, and this script just finds where you have it mounted and loads your device tree live. Word of warning, currently, although it seems like you can do that on Raspberry Pi, the API is there, the model is compiled, everything is nice and diddly. Kernel even says that device tree overlay is applied. It doesn't work on Raspberry Pi because Raspberry Pi is different. But if you have any other platform, live loading is actually quite nice and diddly. So now we have some sensor and it works, or it doesn't. And we somewhat suspect that kernel developers didn't write a good driver, which is never ever the case. If you really want to implement some driver, please look first at the kernel source tree. There probably is an implementation better than the one you will write, and you can use, because the kernel is GPL, you can use that implementation as a reference, because in my small experience with those drivers in kernel, they are really, really nice. But what do you do when you want to debug it? I said no soldering, and I didn't say, but it would be nice if I could do that without additional hardware. Oh, look, kernel has ability to debug my I2C devices. And it's actually using tracing, the same thing I'm using on my servers to get performance counters. Isn't that nice? I don't have to have a logic analyzer. I can just start tracing and have all the dumps in kernel. Nice. Unexpected, but nice. So let's get to the first cheap board from China. So you bought your ARM single board computer, and you want to add few analog digital converters to it because you are used to Arduino and you have some analog sensor or something, and you found the cheapest one on eBay and bought few, 4, 5, 6, because they are just $1 each. So what do? The same thing we saw earlier. You just compile the model, say the address of the interface, and it will appear just like it did in the last example. So everything is nice. But you read the datasheet of that sensor. And that sensor, other than 4 analog inputs, also has one analog output, which is the top pin on the left, denoted by A out. So you want to use it. Oh, this kernel model is not very good. It doesn't have ability to control that. Of course it does, but how do you find it? My suggestion is actually to search through the sys for either address of your I2C sensor, which in this case is 48, or for the word output or input. And you will actually get all files, because in Linux everything is a file, which are defined in driver of this model. And if we look at it, there is actually output 0 output file in which you can turn output on or off. So we are all golden. Kernel developers didn't forget to implement part of the driver for this sensor. All golden. My original idea was to measure current consumptions of ARM boards, because I'm annoyed by the random problems you can have just because your power supply is not powerful enough. So it's nice actually to monitor your power usage so you will see what changes. For example, you surely will get to that. Remind me to tell you how much power does the additional button takes. That's actually an interesting thing which you wouldn't know if you don't measure currents. So you buy the cheapest possible eBay sensor for current. The right one is the INA 219, which is bidirectional current sensing. So you can put it between your battery and the, I don't know, solar panel, and you will see whether the battery is charging or discharging. Or if you need more channels, I like INA 3221, which has 3 channels, the same voltage, but 3 different channels. So you can power 3 ARM single computers from one sensor if you want to. And of course, once you have that, again, the current is in some file and it will be something. But I promised you IoT, right? Nothing I said so far is IoT. Where is the internet? Where are the things? You know, the buzzwords missing. Okay, challenge accepted. Let's make a button. You know, it's like a blink LED. So for the buttons, because I was not allowed to use soldering iron in this talk, I'm using old buttons from old scanner. Nothing special, free buttons, in this case with hardware debounce, but we don't care. 4 wires, 3 buttons, how hard can it be? Well, basically, it can be really, really simple. This is the smallest font, so if you see how to read this, I congratulate you. In this case, I'm specifying that I want software pull-up in this first fragment on the top, which basically, I could have put some resistors, but you said no soldering. So here I'm telling to my processor, please do me a pull-up on those pins. And then I'm defining 3 keys, as you can see, email, connect, and print, which generate real Linux keyboard events. So if you are in X and press that key, it will generate that key. I thought it would be better to generate, you know, the magic multimedia key bindings as opposed to A, B, and C, because if I generated A, B, and C and was its console, I would actually generate letters on a login prompt, which I didn't want. So I actually did it, and it's quite easy. In this case, I'm using GPIO keys pooled, which means that my CPU is actually pulling every 100 milliseconds those keys to see whether their status changed. And since the board is actually connected through the current sensing current sensing sensor I mentioned earlier, I'm getting additional, how many milliamps? Every 100 milliseconds, pulling 3 keys. 60. I wouldn't expect my power consumption to rise by 60 milliamps because I'm pulling keys every 100 milliseconds, but it did. And because I could add sensors to the Linux without programming drivers, I know that. Why am I using polling? Because on Allwinner, all pins are not interrupt capable. So in a sense, all pins cannot generate interrupts on Allwinner. Raspberry Pi in this case is different. On Raspberry Pi, every pin can be an interrupt pin. On Allwinner, that is not the case. So the next logical question is, how do I know when I'm sitting in front of my board whether the pin can get the interrupt or no? My suggestion is ask the kernel. Just grep through the debug interface of the kernel, through the pin CTL, which is basically the thing which configures the pins on your ARM CPU, and try to find the IRQ, and you will surely get the list of the pins which are IRQ capable. Take in mind that this will be different on different ARM architectures. So unfortunately, on Allwinner, it will always look the same because it's Allwinner architecture, actually Sunxi. But on the Raspberry Pi, for example, this will be somewhat different. But the kernel knows, and the grep is your friend. So you wrote the device tree, you load it either live or something on some other way, you connected your buttons, and now let's try, does it really work? Of course it does. We will start EVA test, which will show us all the input devices we have. The new one is the GPIO 3 buttons, which is the same name as our device tree overlay. And we can see that we see the same things we saw in device tree. We defined 3 keys with these events. But we free of charge got, for example, keyboard repeat. Because this is actually meant to be used for keyboards, our kernel is automatically implementing repeat key. We can turn it off, but this is example of one of the features which you probably wouldn't implement yourself if you are connecting those 3 keys to your Arduino. But this is still not the Internet of Things. If this is the Internet, it should have some kind of Internet in it, some buzzword, for example, MQTT. And it really can. Just install trigger happy daemon, which is a nice daemon which basically listens to input events, and write a free file configuration which will send each key press through the MQTT, and job done. I did the Internet button without a line of code, just the configuration. One side note here, if you are designing some Internet of Things thingy, which even if you are only one who will use it, it's a good idea. But if you are doing it for somebody else, please don't depend on the cloud. Because I wouldn't like for my door to be locked permanently with me outside just because my internet connection isn't working. Think about it. Of course, you can use any buttons. In this case, this was the first try. I actually like the free buttons better than this one. That's why these buttons are coming second. And this board with the buttons has one additional nice thing, and that is the LED. We said that we'll cover buttons and LEDs, right? Unfortunately, this LED is 5 volts, so it won't light up on 3.3 volts. But when you mentioned LEDs, something came to mind. How can I use those LEDs for something more useful than just blinking them on or off? We'll see later then turning them on or off is also useful. You probably didn't know that you can use Linux triggers to actually display status of your MMC card, CPU load, network traffic, or something else on the LEDs itself. Either the LEDs which you already have on the board, but if your manufacturer didn't provide enough of them, you can always just add random LEDs, write device tree, and define the trigger for them. And this is an example of that. And this example is actually for this board, which is from the ThinkPad dock to be exact, which fortunately, which isn't at all visible on this picture, but you will believe me, has actually 2 LEDs. And these 3 keys and 2 LEDs actually made the ARM board, which doesn't have any buttons on it or status LEDs, somewhat flashy with buttons. That's always useful. On the other hand, here I would just want to share a few hints with you. For a start, first numerate your pins. Because if you compare the picture down there, which has 7 wires and are numerated, which is second try, with the first nodes on the up, you will see that in this case, I thought that there was 8 wires. So deducing what is connected where when you have a wrong number of wires is maybe not the good first step. On the other hand, we saw the keys. What about rotary encoders? For years, I was trying to somehow persuade Raspberry Pi 1 as the lowest common denominator of all ARM boards, you know, cheap, slow, and so on, to actually work with this exact rotary encoder, the cheapest one from the AliExpress, of course. See the pattern? I tried Python. I tried attaching interrupts into Python. I tried C code, and nothing worked. At least it didn't work reliably. And if you just write the small device tree, say the correct number of steps you have at your rotary encoder, because by default it's 24, but this particular one is 20, you will get perfect input device for your Linux with just a few wires. Amazing. So we saw the buttons, we saw the LEDs, we have everything for IoT except the relay. So you saw on one of the previous pictures this relay box. It's basically 4 relays separated by optocouplers, which is nice. And my suggestion, since you can't, in device tree, you can't say this pin will be output, but I want to initially drive it high, or I want to initially drive it low. It seems like you can say that. It's documented in documentation. It's just not implemented on every ARM architecture. So you can write it in device tree, but your device tree will ignore you. But you can, and this might be somewhat important because, for example, this relay is actually powering all your other boards, and you don't want to reboot them just because you reboot the machine which is actually driving the relay. So you want to control that pin as soon as possible. So my suggestion is actually to explain to Linux kernel that this relay is actually for LEDs, which is somewhat true because the relay has the LEDs on it. And then use LEDs which do have the default state which works to actually drive it as soon as possible as the kernel boots. Because kernel will boot, it will change the state of those pins from input to output and set them immediately to correct value, so you hopefully won't power cycle your other boards. And then you can use the LEDs as you would normally use them in any other way. If LEDs are interesting to you, have in mind that on each of your computers you have at least two LEDs. One is caps lock and one is num lock on your keyboard. And you can use those same triggers I mentioned earlier on your existing Linux machine using those triggers. So, for example, your caps lock LED can blink as your network traffic does something on your network. Really, it's fun. On the other hand, if you have a Raspberry Pi and you defined everything correctly, you might hit into some kind of problems. That particular chip has default pull-ups which you can't turn on for some pins which are actually designed to be clocks of this kind or another. So even if you are not using that pin as the SPI clock, whatever you do in your device tree, you won't be able to turn off. Actually, you will turn off the setting in the chip for the pull-up, but the pull-up will be still there. I actually thought that there is a hardware resistor on board, but there isn't. It's inside the chip. Just word of warning. So if anything, I would like to push you towards using Linux kernel for the sensors, which you might not think of as the first choice if you just want to add some kind of simple sensor to your Linux. Instead of Arduino over serial port, which I did, and this is the solution with much less moving parts, or wiring Pi. And in the end, once you make your own shield for Raspberry Pi, you will have to write that device tree into the EEPROM anyway, so it's good to start learning now. So I hope that this was at least useful or interesting. And if you have any additional questions, I will be glad to answer them. And if you want to see one of those all-winner boards which can be used with my software to show the pinout, here is one board which Cost actually borrowed me yesterday, and in which yesterday evening I actually ported my software, which is basically just writing the definition of those pins over here and the pins on the header, which I basically copy-pasted from the Excel sheet. Just to show that you can actually do that for any board you have with just really pinout in textual file. It's really that simple. Here are some additional links, and do you have any questions? One. No.